Chemical kinetics is the study of the rates at which chemical reactions occur. Here, rate means speed. Speed involves time. Therefore, the study of chemical kinetics involves time. Note, the SI unit for time is seconds. The rate of a reaction is often called the reaction rate. Recall, a chemical reaction involves reactants and products. Reactants, products. The reaction rate is a measure of the change in concentration of a reactant or product with time. The concentration of a reactant or product is expressed as moles divided by liter, or molarity. From here on, molarity will be expressed in: consider a chemical reaction. A yields B. Initially, at T equals 0, only A is present. As the reaction progresses and time elapses, concentration of A decreases, while concentration of B increases. Graphically, this is shown on a plot of concentration versus time. The rate of disappearance of reactant A is mathematically expressed as rate of disappearance of A equals negative change in concentration of A divided by change in time. Note the negative sign for the reactant. Why is there a negative sign? Recall, delta brackets is the change in concentration. Delta brackets equals final concentration minus initial concentration. As the reactant A is consumed, concentration of A final is less than concentration of A initial. Thus, the change in concentration of A is negative. By convention, rates are expressed as positive quantities. Hence, the negative sign in the rate of consumption of the reactant. Similarly, the rate of formation of product B is expressed as rate of formation of B equals change in concentration of B divided by change in time. Note that there is no negative sign for the rate of formation of products. In the previous example, we considered the general reaction A yields B. From the stoichiometry of this reaction, we can conclude that the rate of formation of B is equal to the rate of consumption of A. Since these rates are equal, either one can be used to define the reaction rate. Reaction rate equals negative change in concentration of A divided by change in time equals positive change in concentration of B divided by change in time. For reactions with more complicated stoichiometry, the rates of formation of products and consumption of reactants may be different from one another. Consider the reaction. From the stoichiometry, we conclude that every time 2 NH3 molecules are formed, 1 N2 and 3 H2 molecules are consumed. The rate of formation of NH3 is expressed as and is twice as large as the rate of consumption of N2 given by. Furthermore, the rate of consumption of H2 is 3 times as large as that of N2. Therefore, we conclude that negative change in concentration of H2 divided by delta T is equal to negative 3 times the change in concentration of N2 divided by delta T, and change in concentration of NH3 divided by delta T is equal to negative 2 times the change in concentration of N2 divided by delta T. These stoichiometric relations imply that we can define the reaction rate as reaction rate equals 1/2 change in concentration of NH3 divided by delta T equals negative change in the concentration of N2 divided by delta T equals negative 1/3. Change in concentration of H2 divided by delta T. For a general chemical reaction, A, B, C, and D are the stoichiometric coefficients. A and B are reactants, while C and D are products. The reaction rate is written as reaction rate equals 1 divided by C times the change in concentration of C divided by delta T equals 1 divided by D times the change in concentration of D divided by delta T equals negative 1 over A times the change in concentration of A divided by delta T equals negative 1 over B times change in concentration of B divided by delta T. The reaction rate thus written has a magnitude independent of whether it is expressed in terms of reactant or product concentration. Consider the balanced chemical reaction. The reaction rate for this chemical reaction is expressed as reaction rate equals negative change in the concentration of HI divided by 2 times delta T equals change in concentration of H2 divided by delta T equals change in concentration of I2 divided by delta T. Note the different coefficients in the expression for the reaction rate. Graphically, the changes in the concentration with time of the reactants and products are depicted as Consider the balanced chemical reaction. An aqueous solution of bromine is reddish-brown in color. Formic acid, Br-, H+, and CO2 are colorless. Add formic acid to Br2 and the reaction occurs. As the reaction progresses, the concentration of Br2 steadily decreases. The rate of this chemical reaction is expressed as rate equals negative change in concentration of Br2 divided by delta T equals negative change in concentration of HCOOH divided by delta T equals change in concentration of Br- divided by 2 times delta T equals change in concentration of H+ divided by 2 times delta T equals change in concentration of CO2 divided by delta T. Example: HI decomposes to H2 and I2 according to the equation. The concentration of HI was measured at various times during the reaction and the following data was obtained. A. Calculate the average rate for the first 20 seconds. From the balanced chemical reaction, rate equals negative change in concentration of HI divided by 2 times delta T. The average reaction rate is the change in concentration of the reactant or product divided by the total time and the stoichiometric coefficient. Average rate equals negative final concentration of HI minus initial concentration of HI divided by 2 times T final minus T initial equals equals 0.00103 moles per liter per second. B. Calculate the initial rate. The initial rate is calculated using data collected at the earliest time of reaction. Here, data at 0 and 2.0 seconds. Thus, rate equals negative change in concentration of HI divided by 2 times delta T equals negative concentration of HI at 2 seconds minus concentration of HI at 0 seconds divided by 2 times 2 minus 0 equals 0.0013 moles per liter per second.
Example, write the reaction rate expression in terms of the change in reactant concentration for the following reaction. Reaction rate equals Write the reaction rate expression in terms of the change in product concentration for the following reaction. Reaction rate equals
Right, try to complete those boxes before you move on when you are watching this.
the synthesis of ammonia is represented by the reaction. Calculate the rate of disappearance of hydrogen when the rate of formation of ammonia is 2.15 moles per liter per second. Reaction rate equals divided by 3 delta T equals equals 3.23 moles per liter per second.
The rate of reaction, or reaction rate, at a particular time is called the instantaneous rate. Example: consider the decomposition of nitrogen dioxide. The reaction rate is expressed in terms of reactants as reaction rate equals negative change in concentration of NO2 divided by 2 times delta T. The experimental data of NO2 concentration as a function of time during the reaction is given in the following table. Calculate the instantaneous rate of decomposition of NO2 at 3 seconds. To calculate the instantaneous rate, make a graph of concentration of NO2 versus time. At 3 seconds, draw a vertical line that intersects the curve. Draw the tangent line to the curve at the point of intersection. Now select 2 points at a reasonable distance from each other on the tangent line. Find the x and y values for each of these points. The difference in x values is x2 minus x1 equals 5 minus 1 equals 4 seconds. The difference in y values is y2 minus y1 equals 0.85 minus 1.46 equals negative 0.61 moles per liter. Instantaneous rate equals 1 divided by coefficient of the reactant times negative slope of the tangent. Slope of the tangent equals y2 minus y1 divided by x2 minus x1 equals negative 0.15 moles per liter per second. Equals 0.08 moles per liter per second.
The rate of reaction or reaction rate at a particular time is called the instantaneous rate. Example: the decomposition of dinitrogen pentoxide is represented by the following reaction. The reaction rate is expressed in terms of reactants as reaction rate equals the experimental data characterizing the progress of the decomposition reaction is given in the following table. Calculate the instantaneous rate of the decomposition of N2O5 at 25 seconds. To calculate the instantaneous rate, make a graph of concentration N2O5 versus time. At 25 seconds, draw a vertical line that intersects the curve. Draw the tangent line to the curve at the point of intersection. Now select 2 points at a reasonable distance from each other on the tangent line. Find the x and y values for each of these points. The difference in x values, that is, x2 minus x1, equals 35.0 minus 12.5 equals incorrect. Try again. .5 seconds. The difference in y values, that is, y2 minus y1, equals .27 minus 0.42 equals incorrect. Try again. Negative 0.15 moles per liter. Instantaneous rate equals 1 divided by the coefficient of the reactant times negative slope of the tangent. Slope of the tangent equals negative 0.0067 moles per liter per second. Instantaneous rate equals correct. Try again. Instantaneous rate equals equals 0.0034 moles per liter per second.
The reaction rate is usually a function of the concentration of the reacting species. Ordinarily, chemical reactions occur as a result of molecular collisions. Thus, the larger the concentration of reactants, the greater the number of collisions in a given time, resulting in a faster reaction. As the reaction proceeds, the concentration of the reactant decreases, and the frequency of collisions between the reactant molecules decreases. Hence, usually the reaction rate diminishes as the reaction proceeds. The relationship between the reaction rate and the concentration of the reactants is called the rate law. For example, consider the decomposition of dinitrogen pentoxide. The reaction rate expressed in terms of reactants is given by reaction rate equals negative change in concentration of N2O5 divided by 2 times the change in time. The rate of reaction is usually found to be proportional to the reactant concentration raised to some power m. Thus, reaction rate is proportional to concentration of N2O5 raised to the power of m, or reaction rate equals K times the concentration of N2O5 raised to the power of m. This relationship is called a rate law. K is called the rate constant. M is called the order of the chemical reaction with respect to the reactant N2O5. Note, never assume M to be the stoichiometric coefficient of the balanced chemical equation. M must be determined from experimental measurements of the rate of reaction as a function of reactant concentration. If M equals 0, then the reaction is zero order with respect to the reactant. If M equals 1, then the reaction is first order with respect to the reactant. If M equals 2, then the reaction is second order with respect to the reactant, and so on. Example. Consider the decomposition of dinitrogen pentoxide at 25 degrees Celsius. The following data was collected. A. Derive the rate law. Reaction rate equals K times the concentration of N2O5 raised to the power of M. In order to calculate M, choose the first two concentrations. Rate 1 equals K times the concentration of N2O5 raised to the power of M. 0.085 equals K times 0.10 raised to the power of M. Similarly, rate 2 equals K times the concentration of N2O5 raised to the power M. 0.34 equals K times 0.20 raised to the power M. Now, divide equation 2 by equation 1. In doing so, you will end up with a number greater than 1. Hence, M equals 2. The reaction is second order with respect to N2O5. Therefore, the rate law is reaction rate equals K times the concentration N2O5 raised to the power of 2. B. Calculate the reaction rate constant K. Choose any concentration, for instance the first, and apply the rate law. 0.085 equals K times 0.10 raised to the power of 2. K equals. Here, it is important to pay attention to the units. K equals 0.085 moles per liter per second divided by 0.10 raised to the power of 2 moles squared per liter squared. Equals 8.5 liters per mole per second. Example. The decomposition of gas A into gas B is represented by the reaction. Using the experimental data provided below, determine the order of the reaction and calculate the rate constant. Reaction rate equals K times the concentration of A raised to the power of M. Apply the rate law to the first data point. .640 equals K times 3.00 raised to the power M. Divide equation 2 by equation 1.
Right, what is the power of 2 here, which is going to be equivalent to M, because that is 1.
Thus, m equals 1. Hence, the order of the chemical reaction with respect to A is 1. The rate law is reaction rate equals K. In order to calculate K, use the first equation. 0.320 equals K times 1.50 raised to the power m. K equals units of K equals moles per liter per second divided by moles per liter. Consider a general chemical reaction with reactants A and B. Here, A and B are the coefficients of the balanced chemical equation. The rate law is expressed as rate equals K times the concentration of A raised to the power of m times the concentration of B raised to the power of n. Here, m is the order of the reaction with respect to A, and n is the order of the reaction with respect to B. The overall order of the reaction is m plus n. Remember, the exponents m and n must be calculated using experimental data of reaction rate as a function of concentration. Example, consider the following reaction at 45 degrees Celsius. The experimental data is given in the table below. A. Derive the rate law. B. Calculate the overall order of the reaction. C. Calculate the rate constant K. Rate equals K times the concentration of CO raised to the power of m times the concentration of NO2 raised to the power of n. In order to calculate m, select two data sets where the value for concentration CO is different and the value for concentration of NO2 is the same. From the data given, one could select data sets 1 and 2. Using this relationship for data set 1, 0.0050 equals K times 0.50 raised to the power of m times 0.050 raised to the power of n. For data set 2, 0.010 equals K times 1.0 raised to the power of m times 0.050 raised to the power of n. Divide equation 2 by equation 1. 2 equals 2 raised to the power of m, or 2 to the power of 1 equals 2 raised to the power of m. M equals 1. This means that the order of the reaction with respect to CO is 1. To calculate n, select two data sets where concentration of CO is the same, but the concentration of NO2 is different. From the data set given, one could select data sets 2 and 4. Using this relationship for data set 2, 0.010 equals K times 1.0 raised to the power of m times 0.050 raised to the power of n. For data set 4, 0.010 equals K times 1.0 raised to the power of m times 0.10 raised to the power of n. Divide equation 2 by equation 1. 1 equals 2 raised to the power of n. N equals 0.
All right. You'll be wondering why 1 equals to 2 raised to power n and n equals to 0. Remember, anything raised to power 0 is always 1. So in other words, if you have x raised to power 0 equals to 1. So what we are trying to say here is 2 raised to power 0 equals to this 1. So since 2 and 2 have the same base, then 0 equals to n. All right? That is mathematics. This is not chemistry.
Therefore, the order of the reaction with respect to NO2 is 0. Thus, A, the rate expression is rate equals K times concentration of CO. This means that the rate is independent of the concentration of NO2. B, the overall order of the reaction is 1 plus 0 equals 1. C, use dataset 1 to calculate K. 0.0050 equals K times 0.50, or K equals 0.01 per second. Note, in the following interactive problems, all numbers in scientific notation must be entered in calculator format. For example, 5.1 times 10 to the 7th must be entered as 5.1 E7. Example, for a reaction, the following rate data was obtained. A. Determine the rate law. B. Calculate the overall order of the reaction. C. Calculate the rate constant K. The general rate expression is the simplest is to select 1 and 2. Write the rate expression using dataset 1. The simplest is to select 1 and 4. The rate expression using dataset 1 is 6.60 E3 equals K times 1.00 E2 raised to the power of 1 times 1.00 E2 raised to the power of n. Write the rate expression using dataset 4. K equals 6.60 E -3 liters squared per mole squared per second.
Consider a general chemical reaction with reactants A, B, and C. Here, A, B, and C are the coefficients of the balanced chemical equation. The rate law is expressed as rate equals K times the concentration of A to the power M times the concentration of B to the power N times the concentration of C to the power L. Here, M is defined as the order of the reaction with respect to A. N is defined as the order of the reaction with respect to B. And L is defined as the order of the reaction with respect to C. The overall order of the reaction is M plus N plus L. Remember, the exponents M, N, and L have to be calculated using some experimental data. Consider the following reaction. The initial rate data is A. Determine the rate law. B. Calculate the overall order of the reaction. Rate equals K times the concentration of A to the power M times the concentration of B to the power N times the concentration of C to the power L. In order to calculate M, typically one would select two data sets where the concentration of B and the concentration of C are the same. However, in this problem, there are no two data sets where the concentration of B and the concentration of C are the same, so that they can be canceled out. Hence, skip the calculation for M. Skipping the calculation of M, we first calculate N. Select data sets 3 and 4. The concentration of A and the concentration of C can be canceled. The rate law for data set 3 is. Similarly, the rate law for data set 4 is divide rate law 4 by rate law 3. Two is equal to 2 to the power n. N is equal to 1. Now we can solve for M selecting data sets 1 and 2. The rate law using data set 1 is. Similarly, the rate law for data set 2 is. Divide rate law 2 by rate law 1. (16) is equal to 2 to the power m. M is equal to 4. Select data sets 2 and 4 to solve for L. The rate law using data set 2 is. Similarly, the rate law using data set 4 is. Divide rate law 4 by rate law 2. Two is equal to 2 to the power L. L is equal to 1. Therefore, M equals 4. N equals 1. L equals 1. A. The rate law is rate equals K times the concentration of A to the 4th power times the concentration of B times the concentration of C. B. The overall order of the reaction is 4 plus 1 plus 1 is equal to 6. Example. Consider the reaction The following initial rate data was obtained. A. Determine the rate law. B. Calculate the overall order of the reaction. The general rate expression is rate equals K The simplest is to select 1 and 2. Write the rate law using data set 1. Thus, M is equal to the simplest is to select 2 and 3. We already know the rate law using data set 2. Write the rate expression using data set 3. Thus, N is equal to we already know the rate law using data set 3. Write the rate expression using data set 4. Thus, N is simplest is to select 3 and 4. We already know the rate law using data set 3. Write the rate expression using data set 4. Hence, the rate law is one. Consider the decomposition of N2O5. The rate law is expressed as rate is equal to K times the concentration of N2O5. This equation relates the rate of decomposition to the concentration of N2O5. However, it does not express the changes in concentration and time. Recall, rate is equal to negative 1/2 times the change in the concentration of N2O5 divided by the change in time. Equating these two expressions, we get this equation is called the differential rate law. The differential rate law is integrated over time. By integrating over time, we relate concentration to time. The rate law is expressed as rate is equal to K times the concentration of N2O5. Here, M is equal to 1. This reaction is called a first-order reaction. This relationship expresses that for a first-order reaction, the rate is directly proportional to the concentration of reactant. For a first-order reaction of the type A yields products, rate is equal to K times the concentration of A is equal to negative the change of the concentration of A divided by change in time. The integrated rate law for this first-order reaction is expressed as the natural log of the initial concentration of A divided by the concentration of A at time t is equal to K times t. Ln is the natural logarithm. The concentration of A subscript 0 is the initial concentration of the reactant. The concentration of A is the concentration of reactant at time t. K is the rate constant. T is time. This expression can be rearranged as thus. Compare this equation to the general equation of a straight line. Y is equal to mx plus b. Rearrange this. Y is equal to b plus mx. Then the slope, m, is equal to negative k. Half-life of a reaction. This is defined as the time required for the concentration of the reactant to decrease to half its initial value. Recall the integrated rate equation for a first-order reaction. At time t 1/2, that is to say, the half-life, thus, or the natural log of 2 is equal to K times t 1/2. Or 0.693 is equal to K times t 1/2. 0.693 divided by K.
All right, you don't have to memorize this formula. T half, that is half-life. The formula is in your formula sheet for the exams. So what I advise you to do is once you are given the question, just go straight to the formulas first and know exactly what formulas are you given so that that will guide you when you come across a question and you have to decide which formula to use.
Thus, two important equations to remember for a first-order reaction are Example: consider the reaction where rate is equal to K times the concentration of N2O5. K is equal to 0.0005 per second at 25 degrees Celsius. Calculate the concentration at 60 minutes, when the initial concentration of N2O5 is 0.01 molar. Note the expression rate is equal to K times the concentration of N2O5. N2O5 is to the power of 1. Hence, this is a first-order reaction. Now, recall the integrated rate law for a first-order reaction. The concentration of A initial is equal to 0.01 molar. The concentration of A is to be calculated. K is equal to 0.0005 per second. T is equal to 60 minutes times 60 seconds per minute is equal to 3,600 seconds. Thus, the concentration of A is equal to e to the negative 6.4 is equal to 0.002 molar. Example: cyclopropane, C3H6, decomposes to give propene by a reaction that is first order in cyclopropane. Rate is equal to K times the concentration of cyclopropane. K is equal to 0.054 per hour, and the initial concentration of cyclopropane is 0.050 moles per liter. Calculate the time in hours necessary for the concentration to decrease to 0.010 moles per liter. The first order integrated rate expression is the concentration of A initial is equal to $30 hours. Example: consider the following first-order reaction. A. Calculate the rate constant when the half-life is 6.3 seconds. Recall T1/2 is equal to 0.693 divided by K for a first-order reaction. Thus, K is equal to 0.693 divided by T1/2 is equal to 0.693 divided by 6.3 seconds is equal to 0.11 per second. B. The initial concentration of C2H5Cl is 0.22 molar. Calculate the concentration of C2H5Cl at 5.0 seconds. The general expression of the integrated rate law for a first-order reaction is incorrect. Try again. The natural log of the concentration of A is equal to incorrect. Try again. The natural negative 2.06. The concentration of A is equal to (0.127 molar at 5.0 seconds). Example: calculate the rate constant in per minute for a first-order reaction that is 40% complete at 50 minutes. Assume that the initial concentration is 100 molar. Since the reaction is 40% complete at 50 minutes, the concentration at 50 minutes is 60 molar. Thus, applying the integrated rate law for the first-order reaction, K is equal to 0.01 per minute, or 1.0 times 10 to the negative 2 per minute. Example: the decomposition of N2O5 is a first-order process, and its rate constant is 1.A. Calculate the half-life of N2O5. T1 half is equal to T1 half is equal to T is equal to
Right, let's stop right here. I think you have enough information on kinetics that should be able to help you where you also practice with the worksheet. Right, good luck, everybody.